Okay, so last Tuesday, we were here and we talked about how we can use the functional dependencies to determine the primary keys, the candidate keys rather. So we'll continue and we will we will we ended up with this example. So I hope you all still remember. Before that, maybe just do a simple example first to recap. Let's look at the. I think this example is good. So let's look at this example where I have a relationship A with four attributes A, B, C, and D. In this, A implies C and B implies D. And so the question then is A, B a candidate key? Is A, B a candidate? Is A, B a candidate key? Okay, so we call what's the first thing to do? The first thing to do is we want to check for all the elements not on the right hand side. So I have two functional dependencies, A implies C and B implies D. And I have A, B, C, D as my attributes. So the first thing to do is really every time look at the right hand side and look for the attributes that are not on my right hand side. In this situation, A and B are not in my right hand side. So it is quite certain that definitely these two will be part of the candidate key. Okay, and let's say if I have A, B, and the next thing I want to do is I want to find the closure of A, B. So recall in my last lecture, we will find a subset of this to see if does it fire off any rule. I will notice that A implies C can be fired off here. So I will have A, B, C, and B implies D. And this is then part of my primary key. Well, this is then my primary key. Can? Okay. Let's try to tweak the question a little bit. By right, the next question is I need to remove B to see if is this key minimal or not. But in this case, actually, I don't need to do it because I'm quite sure that it's going to be minimal because A and B don't turn out on my left hand side. So it is definitely going to be minimal. Are there any questions on this? This was something that we went through on Tuesday. So hopefully you are a bit familiar with this entire process already. Okay, let me see if I were to tweak this example, how would it make it? How can I change it to something that is very different? Something that is a little bit different. I think this is quite a straightforward example. So never mind. Let's move on to the example that we ended off last week, which is this one. Okay, so last week we ended off in this example. So R consists of A, B, C, D, E, F. I think there's G and H as well. So these are the attributes in my relationship R. Yeah, I think there's someone that's not muted. Okay. So these are the relationships that are in my attributes in my relationship R. And the question is, I want to find my candidate key. The first thing that we should be doing is, once again, I want to find the attributes that are not on my right hand side. So we always start off with that. So CH implies G, A implies BC, B implies CFH, E implies A, F implies EG. So the elements that are in my right hand side is A, B, C, D is not, so D is E is here, E, F is also here, G is also here, H is also here. So these are the elements that are, all right, I only have one element that is not on my right hand side. So I'm quite sure at this point, I'm quite sure that D has got to be part of my primary key, or rather, sorry, D has got to be part of my candidate key. So the next thing I do is I find the closure of D. And in this case, the closure of D is just equals to D itself. So there's nothing that I can do from there. And definitely we can tell that D by itself, right, is not going to be your primary candidate key because D does not imply the entire thing. So then the next thing is what then are the candidate keys? So we don't know. So we have to try one by one. So the first thing we do is we try AD. We find the closure of AD. AD closure is going to be A and D, but I know that A implies BC, so I will have A, B, C, D because of this. Okay, so and B implies C, F, H equals to A, B, C, D, F, H. And F implies E, G, A, B, C, D, E, F, H, G. And so it has A, B, C, D, E, F, G, H. And so this is the entire list attribute. So AD is a candidate key. Okay. Okay, so this is the first candidate key that we have found. Okay. So the question is, find all the candidate keys. So we have found AD. So the next thing we want to do is I'm going to find BD. So I have to go through every single one of them in order to determine which are all the candidate keys. So I will have to find BD closure. So BD closure is firstly equals to BD, and then B implies CFH. So B, C, D, F, H. And I know that F implies EG, B, C, D, E, F, H, G. And E implies A, B, C, D, E, F, G, H. And so BD is a candidate key. So far we have found that AD and BD, both of them are candidate keys. Okay. Then we go on to the next one, which is C. So C is what? CD. Closure equals to CD. So nothing can be triggered off here. And so that is all that we can do. CD is not a candidate key. Okay, then let's go on to the next one. CD is not a candidate key. Okay, so CD is not a candidate key. Let's look at DE. DE is D. Okay, DE. We find the closure of DE equals to DE. We know that E implies A, because A D E. Okay, so sorry, before that we know that the candidate keys are A, D, and B, D so far. Okay, at this point of time, I think it was one of your colleagues. I think either Melvin or Marcus. I can't remember which gentleman. Mentioned that actually here we can stop. Why? Because AD is a candidate key already, and so because of that, we know that this implies a candidate key, and so this naturally is also a candidate key. So we can stop at this point of time here. We know that DE is a candidate key, so actually we can stop at this point of time. We don't need to expand anymore. Okay, so this becomes like a short circuit. So this is what we see in the next slide. So D is also a candidate key. Okay, stop that. And then we have DF. In DF, what we have, we find the closure of DF equals to we have this D, E, F, G, and so we can also stop because you know that DE is a candidate key, and so D, A, D, B, D, E, D, F, they are candidate keys. Okay, so there are at least these four, and then we go on to D. So it's what we say, because D is a candidate key, we can conclude that DF is also a candidate key, and can stop there. And then we have DF, we have DG. DG, there's nothing we can do here because DG does not appear on our right hand side. DH also does not appear on our right hand side by itself, and so we can conclude that these two are not candidate keys. Okay, so we know that DG, DH, and CD, they are not candidate keys. Okay, by right, we should also explore these three combinations together. So C, D, H. If let's say we look at C, D, and H, we'll see whether what is the closure of them. We have C, D, H, G. And then we are actually stop there. There's nothing that we can actually go on from there. If you want to be extremely thorough, C, D, G is also nothing you can, don't think there's anything you can do there also from here. There's nothing. And if you want to be really thorough, C, D, G, H would be C, D, G, H. I think there's nothing. CH is equal to G. Nothing. Nothing. Yeah. So that's all. So we know that firstly, the candidate key is going to be AD, BD, DE, and DF. So these are the four candidate keys. And we also know that in the other set of so-called attributes, right? Actually, they don't form any candidate keys. But from this simple example, we can infer something. We can infer that the table seems to consist of two separate groups of data, whereby AD will imply one entire group, but then there also seems to imply whereby CDH or CDH may also imply that of the other group. So there is a possibility of us doing a normalization of this big table. In this topic is something that we would look at in the lecture, I think 14. Yeah, lecture 14. Yeah, but just keep it in mind that that there is a chance whereby there may be some possibility for decomposition over here. I don't know yet, but there's a chance of that happening now. Okay, so I think this is the last time in this. Yeah. Before I go on to the next lecture, any questions? This one you must be very clear, because the next part all builds upon this. All builds upon this. I think after this we will spend some time on the small little tutorial of about 3 questions for today. Yeah, but we need to be very clear on this because I remember last time I went the course, I asked people about closure. So the next lecture is on minimal basis. So I asked people about closure, they give me the basis. I asked people about basis, they give me the closure. Then I asked people about like what I said earlier, right, about decomposition. Then they give me functional dependency. So these 3 concepts are the students last run got confused over them. Yeah, so maybe not enough practice or whatever, but they really got very confused until it's like I ask you for A, then but the answer given to me is actually like for example functional dependency, which is not correct. So yeah, so these are the 3 concepts that you want to be very familiar with. And functional dependency, we went through then today and last Tuesday, on Tuesday. Yeah, so something that and the next part on minimal basis, right, will build very heavily on the functional dependency. Okay. So we will go on if there are no other questions. So the next part is this is just some background. So given a certain functional dependency, so there are some functional dependency that may be inferred from it. So for example, A implies B, B implies C, A also implies C. Okay, so this was what we went through in the last lecture. So then there is a problem. So okay, no, sorry, before we go and talk about the problem, we talk about what does it mean to be have a closure of a functional dependency, a closure of F, where F defines a set of functional dependencies we have connected. When we talk about the closure of F, right, it is the set of all the functional dependencies that can be derived from F, which is the entire big set, which is very, very big, definitely very, very big. So I will show an example later. These are the 3 assignments that we showed earlier, last lecture, and together with them, the lemmas. So I don't go through them again. So let's look at the first example, A, B, C, D. A implies B, B implies C. The functional dependency would include all the following. The closure of F would include all the following. So this is a huge thing. So firstly, all those in my right-hand side, left-hand side equals to 1. I have to list out all. All those on my left-hand side equals to 2. I also need to list them all. Okay. All those of my left-hand side equals to 3. I also need to list them. All those left-hand side equals to 4. I also need to list them. So basically, every single thing has got to be listed. In this case, right, when I list them, notice that I only list items on my right hand side with only one element. So I don't need to list elements that are more than one. So I just break it down to one element on my right hand side. Okay, so in quizzes or exams, I will not ask you for this because this is ridiculous. So yeah, so I will not ask you for this. But we need to understand what does it mean to have a closure of the set of functional dependencies. Yeah. Okay. So I hope this is clear. Okay. Okay. So the next thing is another. So yeah. So this is to generate the set of functional dependencies. So for every possible attribute X, you compute the closure. Yeah. So you just compute the closure for every possible attribute set of X. So that's why we have left hand side equals to 1, equals to 2, equals to 3, equals to 4. Yeah. So for every single possible set, we compute the closure of X. Okay. So I have another example over here. So this is where my left hand side equals to 1. So by right, I should break down this. A implies A implies A implies B implies C, B implies B implies C, C implies C, D implies D. Yeah. So by right, I should break them down into just single elements, like what I did over here. Yeah, but I didn't do it. Yeah. So by right, I should do it. Yeah. So yeah. So again, this one is how put it? Yeah, it's very tedious to calculate. Not difficult, just extremely tedious. So I will not test on this kind of things. I may test on this. Yeah. So I may test is AB implies E in F plus not. So to do that, actually is very simple. We just calculate the closure of AB. Yeah. So we calculate the closure of AB, which is what we've been doing all along. So I know that A implies D, so I have A, B, D. So D implies E, so equals to A, B, D, E. So A, B, let's do it. Let's do everything. AC implies B. There's nothing here. So at least I know that AB closure AB is A, B, D, E. So if I have single elements on my right hand side, A, B implies E, yes. So this is in class. Oh, yeah, remember my tendency is correct. Thank you, Ryan. Okay, so okay with this example. Okay, let's look at the second one. D implies C is in F plus. So same thing, we just compute the closure of D, and this is going to give me D E. So D E is here. There's nothing here. Nothing here. Hey, wait, AB implies C. Sorry, I didn't see this one just now. Sorry. And yeah, so sorry, let's look at this one now. D closure. So DE. So nothing here. So DE is just DE. So DE does not have C. D closure does not have C. So this is no. Okay. So why okay, can so this is not in F closure. This is an F closure, but just now the way I calculated AB closure is incomplete. So I didn't see this condition earlier. So AB implies C. So AB implies C. So I need one more A, B, C, D, B. So AB is a candidate key. Okay, okay so far. Okay. Yeah. So this is it. Maybe just to do a test, not test, but just to practice. Maybe the class, right, you all want to try to find what are the other candidate keys in this example. So we have AB. Let's try to maybe you'll take about 5 minutes to find. Actually, I don't know also because this is out of the blue one. So you try to calculate what is the other, or whether are there any other candidate keys in this R A B C D. Yeah, so y'all try to find whether are there any other candidate keys in this. So maybe you take about, I think 3 minutes. I'll start at 8:59. I think there's one more. I think there are two candidate keys here. Yes. A, C. Yes. Very good. Ryan and Sean. Yes, very good. So yeah, I think you all are getting the hang of it. So A B implies is time is up already. Yeah, maybe give you all a few more minutes. But I just write down some of the steps. Step. Okay, time is up. Okay, let's do it. We find what is not on my right hand side. So A is not on my right hand side. A not on right hand side. So I have B on my right hand side. I have C. I have D. I have E. So A must be part of my candidate key. So I find A closure equals to A and equals to A D and equals to A D E, and nothing there. So A is not a candidate key. So I have to find AB closure. AB closure is equals to, I have A, B is implies C, A, B, C. A implies D, A, B, C, D. D implies E, A, B, C, D, E. And this, okay. So I have AB to be my first candidate key. And let's look at AC. AC. AC implies B, A, B, C. and I know that AB is a candidate key. So this is also a candidate key. Let's look at AD. AD, I know from here, I cannot expand out. Closure of this seems to be just ADE. So this is not a candidate key. Let's look at just AE alone. AE alone has E is not on my right hand side. So there's nothing that I can expand from here as well. So you're done. So I only have these two candidate keys. Can you just show the procedure in steps? What do you mean? It just looks like that, but can show the did I show manage to show it in this? Okay, can show. Okay, very good. Thank you. Okay, so yeah, so this is how you do it lah. Okay, can. Very good. Okay, yeah, so this is okay. So we call it this, right? This one, sometimes we got use it, sometimes we never use it. This, sometimes we use it, sometimes we never use it. Whether is it useful or not, actually, I don't know. So this is the next part of this, whereby we want to find the minimal number of functional dependencies that's required. So we call, right, when I look for the closure of the F, right, I have so many things, wow, yeah, it's like ridiculous, right? So now not reasonable to understand, to list out all. So what is really required is that we want to find only the minimal basis. So the minimal set of functional dependencies that can represent all the other functional dependencies that are there. Okay, so the minimum basis is really something like your candidate key lah. So meaning that that set of functional dependencies, right, can define every single functional dependency in my F. And if I remove one of it, right, then one of the FDs there will not be represented anymore. So it is very similar to your candidate key, excuse me, just that in this case, right, we are talking about minimal, functional dependency, and not talking about attributes. Yeah, okay, can. Yes, okay. So let's look at this. There is an algorithm to thank you, Ryan. There's an algorithm to do it. So we split all the right hand side into singleton. So meaning that I want to have, let's see if I have A. So sometimes my pen becomes like that. So sometimes I have A, B implies C, D. I need to split it into singleton. So it will be A, B implies C, and A, B implies D. So this is always step one. Okay, that's always step one. So for every attribute, so I now have a list of singleton F, D. Okay. Now this is the first step. The second step, right, is I want to check if, let's say, if I have A, B implies C, can I simplify this one or not? Meaning that if I have A, B implies C, do I really need both A, B implies C? Why? Okay, so for example, if let's say I have A, B implies C, I have A implies B. So actually, right, if let's say I have these two conditions, right, is this minimal? It probably is not minimal, right? Because I know that A implies B and AB implies C. So actually, right, if I just put this to be A implies C and not AB implies C, I will still get back this original functional dependency. So the second step is actually we need to, and I will show it, when I show the example, it's going to be clearer. But the second step is actually to show that for my for my single FD, am I able to cut off any part of my attribute on my left hand side to make it minimal or not? Okay, so this is the second step. Okay, so right now maybe still a little bit abstract, but when I go through the example, it's going to be a little bit clearer hopefully. So in my step 2, I try to see whether can I simplify the left hand side of this functional dependency. And in my step 3, then from my simplified list of my function dependency, I then decide whether can I simplify and remove any functional dependency or not. So actually may look very complicated, but we are only doing these 3 steps. The first step, whatever functional dependency we have, we first decompose it to the singleton functional dependency. This one very simple. Yeah, so this one definitely can get marks. In the second one is I want to see whether for my attributes on my left hand side, are any of them redundant or not. This would require you to calculate a lot of closures, which I will show later on. And in my step 3, we will then look at the remaining set of functional dependency, and then we will find whether are we able to remove any functional dependency or not. Okay, this step is a little bit more complex. Okay, it is very abstract now, so we will show step by step in an example. Okay, so right now we have this example, A, B, and C, and we have 2 functional dependency. And the question is, find the minimum basis M of F. Okay, so the first thing we do is we decompose to singleton. And we notice that A implies B, A, B implies C. They are both singletons on my right hand side. So we don't need to do anything here. So we are sort of done already. The second step, check left hand side for redundancy. In my first FD, A implies B, my left hand side only has one attribute. So there is no way that it can be redundant. So there's no redundant that we have over there. So we can only check A, B implies C to see if is anything here redundant or not. Okay. And in order to do that, what we do is we have A, B implies C. We check the closure of A. We check the closure of A, and we disregard this one first. We check the closure of A. We find that the closure of A equals to A and B. And at this point of time, we realize that the closure of A includes B. And so B is redundant in this functional dependency. And so we can simplify step 2 to A implies B and A implies C. Okay. So this is step number 2. Okay. Okay. Then we now go to step number 3. In step number 3, so it's like this is what I went through earlier. So first thing, the right hand side is all singleton. So step 1, we don't need to do anything. Step 2, we notice that the left hand side is a singleton. So we don't need to do anything. We just need to work on the AB implies C. And we find the closure of A. We find that AB is the closure of A is AB, and so B is redundant, and so we end up with these two functional dependency. Okay. Okay, so far. Okay, the third step, right, actually is we want to test to see if any of these can be dropped or not. So if we want to test if any of these can be dropped or not, what we do is we have F is A implies B, and then A implies C. Okay, so to test if any of this can be dropped or not, the first thing we do is we first okay, let's look at this one first. We see if this one can be dropped or not. Okay. So to see if this one can be dropped or not, we will consider, okay, so I cancel it like that. So I test if this can be dropped or not. I will imagine first that I don't have this. Okay, then I will look at this functional dependency, or rather I look at the remaining functional dependency, and in this case there's only one, and I will see whether from the remaining functional dependency can I get back this or not. And in this case is a bit obvious, we cannot because only A implies C, there's no A implies B. So it will show that from this, if we don't have this functional dependency, for my remaining functional dependency, I cannot get back A implies B. And so I have to conclude that A implies B is required. Okay. Then I will have to do the next thing. Or rather, I have to test A implies C also. So I have A implies B and A implies C. So right now, I have to imagine that A implies C is not there. And I have to look at the rest of my functional dependency. And in this case, it is again very clear that this is the only one. So A implies B, there's no way you can get back A implies C from this functional from the thing. So we can then conclude that A implies C is also so-called required. So our minimal basis will hence be A implies B and A implies C. Okay, so these are the 3 steps. This one I think I forgot to put in the notes. Yeah, but but this is but this is how we should look at it. Let me think. Okay, so there's also one question. So now this is a bit clear. There's only one path to go because A implies B. So the question is, let's say if I also B implies A. So if I B implies A, then what happens? So I will have, when I do this, right, I will check AB implies C or not. Okay. So if AB implies C, what's going to happen is that I can either, if I have closure of A is equals to AB, and closure of B is also equals to AB. So in this case, right, I can either take for this FD, I can either take F A implies C or B implies C. Either one of them is okay. Yeah, but we will not take both. Even if you take both, right? Oh, okay, or rather I put this. If in the event that you take both, right, at this point of time is still okay. But if you take both, it just means that in my step 3 over here, one of these will be taken away. Yeah, because that is the redundancy of the FD. So one of these will be taken away, and you will just for this course, right? We are not very strict about which one you take away, which one you keep, lah. Yeah, so you take away either one of them, is and in theoretical sense, it's still correct, lah. It's still correct. Yeah. So either one of them, you can, if you put either A implies C or B implies C, it will be correct. If you put both, it's still theoretically correct, but I don't recommend that because you will then have more work when you come into step number 3. Okay, so okay, let's say, right, then this is the final part before we go for the break. Sorry, if we have A implies B and I have B implies A, and I also have AB implies C, right? Okay, let's say from step 2, right, I cut down this already. I know that I have A implies B, B implies A, and I also have A implies C. Okay, so let's say we have this. Okay, if we go with this line of thought, right? Okay, let's look at this. If I have if I remove this one, I find the closure of B. I have B is equals to A B and equals to C. So here, what do we find? I find that A. Sorry. I should be finding A. Yeah. Sorry. I should be finding whether does A imply B still form can this be constructed out from this FD or not? So if I were to take away this one, I have A implies C, I have B implies A, and I realize that I'm unable to construct A implies B from my remaining functional dependency. Okay, there will be an algorithm that I will share later how to do this, but I realized that for my remaining functional dependency, I am unable to construct back my A implies B, and so A implies B is going to be required over here. So A implies B is required. So I have B implies A. Let's say if I remove away this one, I am left with A implies B, A implies C. I actually cannot get back my B implies A here. And so A implies B and B implies A, they are both required. If I were to take away this one and I try to reconstruct back A implies C, I cannot get back A implies C also. So I also have A implies C that is required. So let's say, right, if I went to add in B implies C over here. So let's say, right, if I have B implies C here, but from my this FD, I know that B implies A and A implies C, and so I can actually construct back B implies C from this list of remaining FDs. I will hence know that this is redundant and I will not add it in. So my minimal basis will be equals to this 3. Okay, so so the time actually is time for the break already. I exceeded a little bit. Sorry about it. So I leave you all with this thought, and you all try to absorb and to think through this. And 10 minutes later after the break, I'll come back and I'll go through this a little bit again to reinforce this point. Thank you so much. I'll talk to you in a while's time. Thank you. Okay, so where were we just now? We did not go through this example. Okay, so we went through this example, and we also edited a little bit of the example to show more. Okay, so right now we will not formally, but we will do a few more examples to reinforce what we went through earlier. and hopefully you'll be a bit clearer. Okay, so I have now the relation A, B, C, D, E, and these are the following FDs that we have. These are the FDs. So step 1, we always convert everything to singleton. So every time we see this, we convert everything to singleton. So so I have A implies D. So BC, I have AD. So that's why I split into 2. So BC implies A, and BC also implies D. C implies B, E implies A, E implies D. So there's nothing much for me to do there. So you see, if this kind of paper come out in the exam, in the test, right? You write down this, but this online. Yeah. Okay, yeah, but just do your working, yeah. So last time if it's paper, you put down this one, actually got marks already. Yeah. So actually easier to score. The next thing, so this is step 1. Step 2. Step 2 is check if any of the FDs right hand side can be is redundant or not. So this nothing to check for this 4. We only need to check for BC implies A and BC implies D. And it's good in the sense whereby it's B and C for both. So the first thing I do is I check my so I assume I don't have this, and I will check my B closure. My B closure is equals to my B, and that's all. Is it? That's all. Yeah, that's all. And let's look at my C closure is equals to my BC. So my C is able to imply B. And so it says that my B is redundant in this. Similarly, if I do this this one, I will also find that my B is redundant. Okay, in this example, right, it just happens to be the case whereby this redundant. Yeah, it happens to be the case. I would still recommend that you do a check to check to see that actually it's really redundant. Yeah, but in this example, it can be inferred that in both B is redundant. So in my step 2, what my output will be C imply A, C imply D, and all my other 4 functional dependency. Okay. So this is my second step. Okay. Now we have to go to our third step. Third step is I now have 6 individual functional dependencies. And now I have to check to see if any one of them is not required or not. So I think in my notes, I name it incorrectly. I don't know, did I name? I think I named it incorrectly. Yeah, so this is actually 2-2. So I have 6 different functional dependency. So the first functional dependency I want to check is, let me write down all first. I have 6 A imply D, C imply A, C imply B, C imply B, E imply A, and E imply D. So I want to check this one. Okay, So just now we only have 3 variables, so it's pretty trivial to check. But sometimes we have a lot. So if we have a lot, right? So the easier way that, or rather the algorithm to check it is, in fact, we take the left hand side, in this case is A, and we find the closure of it. Okay, so sorry. If I want to check that, I first imagine that I don't have this. I imagine I don't have this FD. Then I take the right left hand side of this FD and I find the closure of it from my remaining FDs that are here. Okay. So when I do this, I find that the closure of my left hand side is still equals to A only. So I don't have A implying D coming out from all my other FDs. And this would imply that A implied D is a required functional dependency. Okay. Okay, let's look at now at the second one. So second one, once again, I imagine that this is not there. And I find the closure of C using this. The closure of C is equals to, first I have C, B from here, then I have D from here. And that seems to be all. Do I have one more? Yeah, C, B, D, yes, that's all. That seems to be all. So my closure of C does not have A. So it means that this is also required. Okay, if we look at the third one, right, is also C, but we have to calculate the closure again. Because right now we are imagining another FD that is not there. So I have to consider now a different set of FD. So the closure of this will be different. So I need to calculate again the closure of C using this set of FDs. And in this case, my closure of C is equals to A, B, C. And I know A implies D, A, B, C, D. So do you notice anything? You should. Is it very lame? Anyway, you should notice that the closure of C has a D. And so the closure of C in this functional dependency, when we're checking on this, has a D, and it means that this is actually redundant. Meaning that if we don't have this one, we are still able to get back the functional dependency C implies D. And so this is then redundant, and so I don't need this. So this is not required. Okay. Okay, let's look at the next one, which is this. No, I've already cancelled this one, so I don't need to consider that anymore. So C implies B. So I'm going to assume I don't have C implies B, and I find the closure of C. And the closure of C is going to be A, C, and and I don't have B, and so the is this is required also. Okay. So the next one will be this one. I will consider this FD, and I will find the closure of E. The closure of E is equals to D E, and that is all. You notice that it does not give me back D implies A, and so this FD is also required. And the last one is E imply D, and I'm going to find the closure of E, assuming I don't have this. E imply E closure is as A, as E, but I also know that A imply D. So this is equals to A, D, E. And at this point, you notice that even if I don't have this functional dependency, D is present, and so this is also redundant. So my minimal basis is equals to A imply D, C imply A, C imply B, is this form. Okay, so this is how we solve this very long question. Any questions on this? It will be clearer as we go through a few more examples. So right now, maybe it's still very new to this concept. But as you practice a little bit here, then you will be a bit more used to this. Okay, let's go through this already. Okay, let's look at this example. Okay, this example, we first have A, B, C. The first thing we do is we find the singleton. So in here, the singleton is A. They're all singletons already, both on my left and on my right hand side. So it means that if they're all singletons here, I don't need to do step 1 and step 2 because they're all done already. So step 1, all are singleton, so I don't need to do anything. Step 2, all the left hand side are also singleton, so I don't need to do anything also. So if we go directly into step 3, where we consider if any of the functional dependencies are redundant or not. So let's look at the first one, A imply B. So do you want to do it? Maybe you'll try, maybe you'll try. You'll give your maybe 1 minute to see if is this redundant or not. Maybe until 9:48. Okay, now it's time for it. Okay, let's do this together. So I'm going to assume that, let's say I do have this, and I find the closure of A. The closure of A will be from all this. So I have equals to A and C. So closure of A is equals to A and C only. And so A implies B is not there. And so this then is required. Let's look at the second one. So I'm going to assume that I don't have this. I find the closure of my left-hand side. Closure of my left-hand side from all the rest is equals to B and C from here. But I also know that B and C, C implies A from here. Correct. B implies C and C implies A. And so the closure of B has A inside here. And so it will mean that this is hence not required. Then I'm going to look at the next one, which is this. So if I assume I don't have this, I find the closure of B. The closure of B, if I don't have this FD, is only equals to B. And so this is not preserved. I mean, I don't get back this from all the rest. And so this is required. And now consider this FD. I find the closure of A, if I don't have this, equals to A, B, and A implies B, B implies C. And so this is within my closure, and so this is also not required. Last one, I will use this. Check if this is required or not. I will assume I don't have this. I'll use this tool to find my C closure, which is equals to just C alone. There's no other thing on my right hand side, left hand side, sorry. And so this is required. So the minimal basis is A implies B, B implies C, C implies A. Can? So this is how we solve this question. Okay. So I think this is what I talked about. So yeah. So this yeah. So I check the first this is required. I check the second one. The second one not required. The third one is required here. And then I check this is the fourth one not required. The fifth one is required. So this is how we solve this question. Okay. Let's look at the next example. And I think you all try this example because this example is requires all the steps. So maybe you all take I think 5 minutes enough. You'll take 5 minutes to maybe you'll try for 5 minutes first. Then yeah, then after that I see if how far you are at. Then we'll let's try 5 minutes first. Yeah. So maybe at 9:57. So maybe we do step 1. Or maybe step 1 and step 2. Yeah. Step 1 and step 2. We do until step 2 for 5 minutes. And then we'll reconvene at 9:57. And then we move on together from there. Yeah, I realized got problem. This one, step 1, step 2 is very simple only. So this one, step 1, step 2 is only A implies A, which we don't need. So maybe you're try to step 3 lah, yeah. Because this one, step 1, step 2 is very simple only. So step 1 is A implies C, B implies A, B implies C, D implies A, D implies B, D implies C. Yeah, so step 1, step 2 is quite trivial. So I think you all just go directly to do step 3. And yeah, I give you all uh, maybe until like 10 p.m. Yeah, 10 p.m. to do the third step. Sorry, thank you. Yeah, A imply A is redundant. Yeah, we don't need to put A imply A. Thank you. One more minute and then I'll start. Okay, it's 10, so I'm going to start. Okay, thank you for your trying. Let's go through this together. Okay, let's do this together. So first thing, I'm going to assume that I don't have this. I will try to recreate this FD from my closure of A. Closure of A is equals to A. There's nothing else of A on my left hand side. And so this is required. Let's look at the second one. If I imagine I don't have this, I'm going to find my closure of B. Closure of B to B. If I'm going too fast, let me know. Now it tells me that my internet is unstable. So, okay, let's look at the third one. I'm going to imagine that I don't have this and look for my closure of B. My closure of B is equals to AB. And I know that A is implies C equals to A, B, C. And so I now realize that even if I don't have this FD, B closure of B is still within can still get me B implies C even without this FD. And so this is not required. Let's look at the next one. B closure is equals to B implies B, which is B, C, D. So from these two, I have B, C, and D. And I also know that B implies A. And so I have A, B, C, D. So that's screw up. Let me check. D definitely implies D. D implies B, and D implies C. And I know that B implies A. So D closure implies A, B, C, and D. And so this is also redundant. Let's look at the next one. D implies, so sorry, consistent. So I find that D closure is equals to, I am going to imagine I don't have this. D closure is going to be equals to C and D. And that is all. And so this is required. Let's look at the last one. The D closure is equals to B, D from here. B implies A, B, D, and A implies C. Equals A, B, C, D. And so this is also not required. Okay, so this is how we solve this problem. So let me check my answer in case I got it wrong. So A1 is required. Second one is required. Third one is not required. This is not required. This is required. Yeah. So fortunately, this time around I'm correct. So okay. Before we go on to the tutorials for the last 5 minutes or so, anybody has any question on this? So I hope you all managed to get this solve this. Yeah, but before I go on, anybody has any question? Oh, okay. If you shuffle, yes, the answer will be different. Yes, correct. So yeah, so the answer will be different if you consider different options. But in the quizzes, we are open to consider all options. But sometimes let's say when I mark I may miss your solution. You know. So if you think that your solution is correct, let me know. Then I'll look at it. And sometimes because there are many combinations, so sometimes I may just miss it. Oh, okay. Okay, all is fine. We'll go on to the wait next tutorial. I did not release this tutorial because I have the solution there, so I never released yet. So I will release it soon. Okay, so this is the tutorial for today. Okay, so question one, B C D D A B C D A B C D. What's the minimum cover? Okay, I think we have time for this. We have time for this. Let's spend. You try this for 2 minutes. You now should be expert already. So try this until 10:08. Then I'll use the last 2 minutes to complete the question. Okay, 10:08 already. So quickly, I have 2 minutes to do this together. So step one, singleton. D implies A, D implies B, D implies C, AC implies D. So this is step one. Step number two, I look at those on the where my left hand side has two elements, AC implies D. So I will first find the closure of A. The closure of A is equals to A and B, and that seems to be all. The closure of C is equals to B and C. That seems to be all. So now from here we notice that the closure of each element A does not contain C. The closure of C does not contain A. So in my step 2, it shows that this is minimal. So I will need to consider all of these FD in my step 3. I have 1 minute to do this. So very fast, very fast. Okay, so let's look at the first one. So first one, A imply B. So I will find A closure. A closure is equals to A. So this is required. Okay, so I will go through this again. I'll go through this very fast now. C closure. I'm going to consider this. C closure is nothing, no other C alone here. So this is also required. I'm going to go through D closure. So D implies B, C, D, and C implies B equals to B, C, D, B, D, B, C, and D. That seems to be all. Do I have A? No, I don't have A. So it seems that this is also required. If I screw up, please let me know. So now I'm going to consider this, which is D closure again. I have A, I have D. And at this point of time, A implies B, and so I am able to use this to generate A, B, D, and so this is not required. So I have, now I'm going to consider this one. So it's D closure equals to, I have A and D. I know that D implies A, and A implies B, A, B, D. And it seems that this is all. I don't get a C anywhere here, and so this is also required. Last question in my last minute that I'm going to eat from you. AC closure. So AC closure is equals to A is imply B and C, and that's all. A, B, A, B, C. Yeah, that's all. And so this is also required. So in my minimal cover, it's going to be A implies B, C implies B, D implies A, D implies C, and AC implies D. Okay, I'll go through this again in D implies A, B, C is also a minimal cover. D implies A, B, C. D implies ABC is also minimal. D implies ABC is also a minimal. Are you assuming that given all things equal, or is it just by itself? So it's saying that this by itself is also minimum cover, is it? Is that what your question is? Okay, maybe I have to check. Probably you went through by another path. I don't, but I will check that. Thank you for sharing. But at least for this path that we are at, it seems that we have this 1, 2, 3, 4, these 4 terms as the minimum cover. Okay, the time is up. Sorry to have taken up extra 3 minutes of your very precious evening. Regardless, I will go through